Hello, and thank you for joining us today. My name is Christy Harris, Director of Technology and Privacy Research with the Future of Privacy Forum. At FPF, our mission is to bring together the wide-ranging views and stakeholders, including academics, advocates, and civil society and companies to identify and bridge the gaps in the privacy space. I'd like to welcome you to the 5th Masterclass session of our year-long Digital Data Flows Masterclass series, developed and presented in partnership with the Brussels Privacy Hub at the University of Free Brussels. We are thankful for their collaboration and support. The goal of this series is to provide an introduction to challenging tech subjects at the heart of the privacy debate. We are not discussing the policy. We instead leave that to you, the policymakers. The topics for our 8-session series are based on highest interest to regulators. As with past sessions, today's session will also be recorded and will be available on our website along with the slide presentations. If you haven't seen the previous sessions introducing artificial intelligence, location data, de-identification, and ad targeting, I encourage you to visit the fpf.org/classes and check them out. Following this session, which is currently being recorded later, you will also be able to find the slides and presentation from today. So today's session is an introduction to the challenging tech subjects. Today's session is an introduction and a deeper dive into the technology of mobile apps. This is an area that is near and dear to me from my previous corporate work and continues to be one of my primary focuses at FPF. Smartphones, tablets, and other mobile devices are used extensively by adults and children and businesses. Given the extensive media attention we're seeing daily in this space, both good and bad, as well as various regulatory efforts across the globe to learn and understand the mobile ecosystem and to draft meaningful policy in this space, I believe this is an especially timely topic for today. I'm especially excited to introduce our 2 experts joining us today, one with a deep public interest in academic researcher from Carnegie Mellon, and also a practical, on-the-ground developer of architecture and security from Mattel. Daniel Smullen is a software engineering PhD candidate at Carnegie Mellon University Institute for Software Research. His focus on privacy and security research includes working with the FTC and the California and New York Attorneys General. Related to mobile app compliance, and he's written a number of notable papers on the subject. His most recent relevant experience and expertise stems from research on projects such as those involving the scraping of over 1.7 million apps on the Google Play Store, followed by automated analysis to determine potential compliance issues. Since his primary interest is in software engineering, and he also has experience in developing apps for the various marketplaces. Also joining us is Faris Alraie. Faris is an expert in the privacy, security, and technology space and currently serving as the Chief Information Security Officer at Mattel, where his areas of focus include corporate security, architecture and engineering, security event management, and incident response. Prior to his role at Mattel, Faris was Chief Information Security Officer and Vice President at Vituity MedAmerica, as well as Visa, where he led similar roles. Faris currently serves on a variety of client advisory boards for security companies and products, where he shares his experiences driving the adoption of leading cybersecurity technologies and audit-level compliance. We are grateful to both Daniel and Faris for being able to join us today, and I think you'll agree that they will both provide very relevant viewpoints and information on this subject. Today's session will be divided into 2 parts. The first, introducing basic concepts and terminology, as well as some more in-depth discussion of platforms, apps, and data permissions and flows. And that will be followed by time for some questions and answers. Part 2 will cover topics including identifiers, third parties, and security, and will also be followed by time for Q&A. Just a few housekeeping notes. Please feel free to ask questions throughout the session by typing them into the chat area in the Zoom platform. While there's no audio capability for the attendees, one, I do appreciate your attendance and your participation, and we'll be monitoring this area, so we will ask any questions that are entered on your behalf. And with that, I'll hand it over to Daniel to jump into part 1.
All right, thank you very much for that wonderful introduction. So once again, my name is Daniel Smullen, and I'm here today in Pittsburgh, Pennsylvania, and I'm going to be beginning with some basic concepts for everyone today. So as was mentioned before, we're going to go in a very broad overview from apps to APIs. We're going to cover some of the mobile operating systems, in particular the two most popular, that would be Android and iOS. And we're going to go into a little bit of detail about how they work, what they are, and what kind of things they provide. And then we're going to talk about permission data versus non-permission data. I think this is probably one of the most important privacy issues, in particular as it pertains to mobile operating systems. But we'll get into that in just a moment. And then finally, we're going to be talking a little bit about the design of APIs, or application programming interfaces. And we're going to talk a little bit about software architecture, what that means, what it entails. And we're going to talk about some software architecture quality attributes, such as scalability, reliability, and data portability. And I'll try to keep things grounded as often as possible in concrete examples. I think they're the most helpful to kind of keep people's attention focused on the concepts as they're most familiar to them. So with that said, let's begin with some basic concepts. So I'm going to be going over what mobile apps actually are, and then I'm going to be drawing a few distinctions here. We're going to be talking about the differences between hardware and software, and then we're going to go a little bit deeper and talk about the differences between source code and software. This is a very important distinction, and this distinction can often be confusing, but we're going to try to make it a little bit less confusing today. Next, we're going to talk about a couple architectural components. Specifically, we're going to talk about the front end versus the back end of applications. And then we're going to talk about the concept of what a walled garden is. So let's start with mobile apps. So what is an app? I mean, I think most people who are attending today probably have a smartphone. And they're probably familiar with, the icons, and maybe can cite various examples of apps, as you can see on the left-hand side of the screen. But what actually is an app? Well, an app is a piece of software that runs on a mobile device. But it can potentially be much more than that. The classical definition of an app also included software that would run on your desktop machine. Now, we're not going to focus so much on that today, because naturally the subject of our discussion is going to be the mobile ecosystem and the mobile context, which, by the way, is enormous. You can see right in the middle of the screen that the mobile operating system global market percentage, Android is probably the most popular at around 76%. The second most popular is iOS. And just to cite a couple more statistics here, the Android ecosystem currently has over 1 billion. Some people are talking about potentially more than 2 billion users. So we're talking about a very, very large number of people that are using these apps. Now, apps run on smartphones, they're software, and they're distributed through app stores. So the Android App Store is where you obtain Android apps, and that's run by Google. It's also known as the Google Play Store. And the iOS App Store, also known as the Apple App Store, is where you obtain iOS apps. And naturally, one cannot download Android apps for iOS or vice versa. Well, that is to say, without doing a lot of hacking and so on. So maybe developers can do this, but it's not typically intended for end users to do this. So typically what happens is applications are developed for a specific mobile OS market, and they're distributed as such. But it's also true that there are cross-platform apps that can be developed for multiple mobile operating systems and can run on both. But the distinctions between the two are actually quite subtle. And I think we'll talk about that a little bit more as we go into the details of the front end versus the back end. Now, it's also true that there are emerging app ecosystems as well. So for example, Google has recently put out the Wear OS, which is specifically intended for smartwatches. And I believe that Apple currently still releases a variant of iOS for their smartwatches. But essentially, these are intended to be operating within the same ecosystem. Though it is true that you can actually connect Wear OS devices to iOS phones and vice versa. So moving on, let's talk about the differences between hardware and software. So I gave several examples already of hardware. I also gave several examples already of software. But the key distinction is as follows. Hardware is a physical thing that you can hold in your hand. Software, absolutely you cannot. In fact, software is often a very difficult concept to understand because it relies on abstractions, ideas, ways of describing inherently very complex systems, but in ways that are hopefully communicatable between one another. So there's a whole variety of different types of software, but generically what it means is essentially binary instructions that run on hardware that tell that hardware what to do, whether it's to display an image or process arithmetic operation like 1 + 1, or when you aggregate many of these operations together, you can get the type of software that we see in mobile apps. But there's other types of software too. So for example, there's system software. We can talk about things like the operating system itself, which is a form of software. There's software that software developers use to develop software. One example of one of them is a tool that's used to build software, such as compilers. There's also very low-level software, for example, that does very utilitarian things on hardware, such as disk formatters. There's very basic software that I'm sure we're all familiar with, such as text editors and word processors. And then, of course, there's utilities that help the device to operate more efficiently, things like memory managers and so forth, which help you manage the storage on your devices and things of that nature. Often, software can be developed specifically with humans in mind, and other forms of software are developed with software developers in mind, or other pieces of software infrastructure, so to speak, is developed with other software in mind. So one form of infrastructure targeted to developers is programming software, tools to aid developers in writing programs. One example of this is called an IDE, or an integrated development environment, which essentially takes text editors, compilers, and potentially other tools that developers can use to analyze software and mushes them all together into a tool set that they can use to effectively program apps and to release apps and to test apps. And then, of course, there's the apps themselves, or application software. Of course, app is short for application, and it's intended to actually perform tasks. So there's things like games, there's educational apps, but there's also productivity apps, things like spreadsheets. All of these things are just forms of software. They're the final artifacts that are often products that can be delivered to someone. But again, not hardware. Software, while it might come on a physical medium, sometimes, way back when, like on a physical disk, for example, those disks themselves are a form of hardware. But the software is the instructions that lie on that hardware, that run on that hardware, that are stored on that hardware, that execute on that hardware. So, as I said, there are many different types of software. Let's talk about the distinction between source code and software. So the difference is subtle, but very important. Source code is the stuff that developers deal with. Now, that is to say, they are still instructions that end up getting executed on hardware, but source code is intended to be human understandable. And so the idea is that the source code is intended for developers to understand, and for developers in order to be able to cognate, such that they can formulate the instructions in such a way that the program runs the way that they desire. And there's a variety of infrastructure that is intended for managing and supporting the development of source code, whereas the software is the end product. And there is quite a bit of difference. So part of that difference can be illustrated in that table that you can see on the left-hand side. You'll see that there's a matrix here. There's free and paid. There's open source and closed source. Now, I'm sure some people have certainly heard of open source. Maybe some more have heard of closed source. Let me help illustrate the distinction. So open source software is software where the source code is readily available to the public. That means that people can actually see the instructions that the developers have put together in order to give the software its functionality. So what that means often is that the source code can be modified and that it can be redistributed. However, just because it's open source does not necessarily mean that it's free. So one example of free open source software is GNU plus Linux, which I'm sure many people have heard of, certainly. And what it is it's a desktop operating system. In fact, Android is based on a variant of the core components of this operating system. But fundamentally, the GNU plus Linux package is free and open source, or FOSS, as us nerds like to call it. Now, the important thing about it is that because it's free, it means that not only is the source code readily distributed, but also the final artifacts, those that you can actually run on your machine, the compiled source code, the executable source code, that is also distributed freely. Now, there are also paid open source software packages as well. And one example of this is Ubuntu. Ubuntu is another Linux-based operating system, and it's becoming increasingly popular as many European governments actually adopt using Ubuntu on the machines, the desktop machines that they run in government offices. But Ubuntu, while there are free versions available, so-called community editions, there are also paid versions of this open source operating system. And essentially what you pay for in the case of Ubuntu is support. When you pay for an enterprise version of Ubuntu, you get additional support on the behalf of the Ubuntu developers at the company Canonical, who will help you resolve issues, fix bugs, and do things that are outside of the purview of their ordinary agenda on your behalf because you're paying them to do it. Now, on the other hand, there is closed source software, much of which is free and much of which is also paid. And good examples of free closed source software are Google Maps and Apple Maps. These applications are closed source because you cannot get access to the source code. That means that you cannot readily modify these apps. You cannot readily modify and redistribute these apps. However, you don't pay for them. So you get to take advantage of the services that Google Maps and Apple Maps provides to you for free without paying for it. Now, another example of a paid closed source app is Microsoft Office, which I'm sure many of us are familiar with. Microsoft Office also cannot be readily modified and redistributed, and we do pay for it. So in a sense, it's the most traditional type of product where you cannot open it up and do things to it to change it. And you also can't necessarily have a look at all of its basic underlying functionality because that's proprietary, and that's why it's closed source. Now, there's a few other concepts I want to briefly mention here. There are source code repositories, which are tools that developers use to manage and keep track of versions and also distribute their source code. One example is GitHub. There are many others. There's GitLab, SourceForge. And then there's also programming languages. Programming languages are the languages in which source code is written. So some examples are C++, Java, Swift, Python, JavaScript. Programming languages, as I said, these are the language in which the source code is written. But while it is still correct to say that software is written in a programming language, again, I want to impress that the distinction is that when we are referring to software, we are often referring to the final compiled or distributable versions of these artifacts. And then finally, as I mentioned earlier, there are also development environments or integrated development environments. And some examples of these are Xcode, which is used to develop applications for iOS. And another example is Microsoft Visual Studio, which can be used to develop applications on a variety of platforms. Another example is Eclipse, which is also free and is used to develop Android applications and also applications on a number of other platforms too. So we've talked about hardware, we've talked about source code, we've talked about software. Now let's talk about some features of software architecture. And two key concepts of software architecture I want to talk about are the front end versus the back end. Now, when I refer to the front end of an application, I'm referring to the client-facing or the client-side components of it. So what this refers to are the software that provides the app with its visible style, with buttons, with text, with colors, with navigation menus, with all of the things that an end user would need to actually interact with it. And there are many, many different types of front ends. In fact, most apps that you have on your phone are just front ends, as distinct from the back end, which we'll get to in just a moment. But there's other forms of front ends too. In fact, apps aren't the only examples of front ends. Websites are often front ends as well, because a website is yet simply another way of interacting with a back end. So what is a back end? Well, a back end, which is often called the server-side component of an application, is where all the machinery and computation and all of the data are often stored, and where all of the data processing usually takes place. Now again, to be clear, these are abstractions. And so when I say front end and when I say back end, I'm really using that as shorthand to describe a potentially very, very complicated collection of software that's working together in order to provide you with these features or with these services. But on the back end, typically what we're talking about is a number of servers that are hidden away in some data center somewhere. They could be potentially anywhere in the world, connected to via the internet, and that the front end interacts with. And a common example of the way that software developers describe these types of systems is actually seen in front of you right now, where simply boxes and lines connecting those boxes together are used potentially on a whiteboard or potentially in more formal types of software blueprints to describe how these components are actually laid out, where they are, who owns them, what they do, and so on and so forth. Now, we won't get into the sort of extreme levels of detailed software design today, but it is important to point out that these details are immense, and they are the purview of software engineers that have to do a great deal of planning and testing and have to have a lot of inherent knowledge to make the design choices about how to formulate a good front end, how to formulate a good back end, and how to formulate a good software architecture that takes all of these various components and puts them together in a way that behaves in the way that users expect. So let's talk a little bit about walled gardens. Now, walled gardens refer to a specific type of software ecosystem. So you'll recall that I talked about the differences between free and paid or free and proprietary software and the differences between open source and closed source software. Now, it's not to say that a walled garden has to subscribe to any particular one of those four types of software distribution modes, but it is important to point out that they sort of tend to correlate a little bit here. So there are two very popular app distribution platforms out there that I've already mentioned. There's the Apple Store and there's the Google Play Store. And the most important distinction between the two is the philosophy in which the proprietors of these app stores use to determine what apps are suitable for distribution on these app stores. And this is probably the most fundamental concept of what belies a walled garden. The Apple ecosystem requires an intense level of scrutiny before developers are allowed to actually put something on their app store. People have to pay to do this. And the Apple ecosystem requires them to follow different but specific developer guidelines compared to the Google Play Store's developer guidelines. And so what this creates is an ecosystem in which if you want to do business with the Apple App Store, and if you want to distribute your app on the Apple App Store, it's very important that you follow their guidelines. It's equally important that you follow the guidelines on the Google Play Store. However, the Google Play Store is not a walled garden. The reason why is because the Google Play Store is free, and there's no specific requirement to pay in order to get access to the Google Play Store. And for that reason, it's extremely popular, and there are literally millions of apps on the Google Play Store. There are also millions of apps on the Apple App Store as well too, but the Google Play Store shows extreme growth. Sometimes this can lead to problems, however, because the number of apps that end up on the Google Play Store can sometimes not be subject to the same level of scrutiny. That's not to say that there's anything wrong with them. What it means is that developers can potentially shorten the time that it takes to get their applications out there into the wild, and they don't necessarily have to pay to do it. So what that often means is that the Google Play Store has a certain reputation for being free, but the Apple App Store has a reputation, which is rightly deserved, for being a walled garden, because you have to pass over this wall, so to speak, in order to participate in this ecosystem. There are other examples of walled gardens as well. However, there are also many, many other examples of software ecosystems which are not walled gardens, such as the various Linux distributions that exist. So it's an important distinction, and it has a lot to do with free versus paid and open versus closed source. But fundamentally, what the walled gardens are about is about determining what's required in order to be able to distribute your app on one platform versus another. And that's aside from the technical considerations. All right, so now, let's talk about the data that you see within these mobile ecosystems. So both iOS and Android as operating systems provide both software developers and the end users, both front-end and back-end components. And one of the important back-end components that both of these operating systems provide is a way of programmatically, that is to say, using software, ways of managing which apps get access to what data. And of course, the front-end component of this permission management system enables the end users to enact their preferences or to provide consent for these apps to access the types of data that's moderated by these permissions. So you can see on the left an example of the iOS permission management system, and you can see on the right an example of the Android permission management system. Now, these permissions, generally speaking, are moderated on a per app basis. So an example on the right, when you see Twitter there, that means that you can give the Twitter app on your mobile device access or not to the camera, contacts, location, microphone, phone, and so on. Now, what these permissions actually entail is quite a bit more than what they say at face value. For example, the camera might literally give access for the app to using the features and facilities of the camera, but there's potentially much more data that can be available, that can be proffered by these permissions. For example, what does it mean when you can actually get access to the microphone versus the phone? It seems like there's not really much difference, is there? Because on a mobile device, when you're talking on the phone, you're certainly using the microphone. And so therefore, there must be some difference. And that difference can be subtle. And it's also very important to note that that difference is mostly directed at application developers, so that those developers can keep track of what it is that their apps need access to in order to provide their functionality. You can see other examples of this on the Apple example on the left. You can see that it provides access to things like photos, whereas on the Android version, you can see that you can get access to camera and storage. So naturally, there are also distinctions between how the two operating systems actually allow developers, and therefore by proxy end users, the ability to moderate access to these different facilities of the device. So I'm going to give a little bit more concrete examples of the different types of permission data in just a moment, but I want to make sure that it's understood exactly what these permissions mean. It means that the app is allowed when the user gives permission, and there are prompts that pop up when the apps request access to these for the first time, access to the various permissions of the device. And you can always go back and change them later, although to be fair, my research often shows that people generally don't tend to do this. But you can, the options are available, and the options are different per app, depending on what it is that the app developer's software that they've written for the app actually requests access to. Now, the problem here can often be that developers don't always know exactly what it is that they've requested access to. Well, why would that be? Well, I think that this is something that we're going to talk about a little bit more detail later, but software is composed of many, many different components, some of which are off the shelf and provided for developers in order to develop software more easily, more quickly, because then that way they don't have to develop themselves all of the functionality that their apps need. But the issue is that sometimes the functionality that these apps request, or rather that these apps are using, comes as a result of the usage of a third-party library. And that library might have source code in it that requests access to these permissions in a way that the developer of the original app didn't know about, maybe because they didn't read or understand the documentation for it well enough, or because they just simply didn't care to check. And it happens often because permissions are complicated and writing software is complicated, and this is not an easy task. So let's move on from that for just a moment.
Daniel, do you mind if I jump in with a question for a second?
Of course.
You showed a sample of permissions that probably most people who have actually used apps or used an Android or an iOS device are familiar with. Are there permissions that are not surfaced to the user or different data elements that an app might have access to without having to explicitly get permission or have permission controls?
Yes, there are indeed. And now, that's not to say that the user doesn't have some modicum of control over these permissions, but it is true that there are categories of permissions which the user does not have the ability to control after the app has been installed. So to be clear, the user fundamentally has control over all of these permissions, but in, well, sort of a ham-fisted way. If you don't want an app to have access to the permissions that are not listed here, that are consented to by purely installing the app, then you simply don't install the app. But there are many examples of this. So one example is getting access to Bluetooth in the case of Android. You don't necessarily need to give direct consent to Bluetooth, for Bluetooth rather, on apps on Android, because that is a permission that you give to the app by installing it. And you give your consent to doing that when in the Google Play Store, you choose to install the app, and then a pop-up appears. That pop-up will tell you what the full gamut of permissions are that the app could request. And this does indeed include permissions that are not controllable after the fact. And you can kind of see a hint to this actually on the bottom of the screenshot on the right, additional permissions. So these additional permissions are ones that the user has consented to by installing the app. Now, in the case of iOS, the same is also the case, but the way that they're explained is slightly different. But there are many, many examples of these. And in fact, there are dozens of permissions that are available on the phone. And by installing the app, you are implicitly, and in many cases explicitly, giving consent for permission for the app to access all of the other permissions that are not explicitly moderated by those that you see in front of you here. But then the others are those that you see in front of you here. And so if you choose to revoke consent for these, then you can do so. You simply go back to the Permission Manager app that's provided by the operating system that you're using. So either the iOS privacy screen or the Android app permission screen, and you can change them. And you can see which permissions different apps have access to. And you can also see the other additional permissions that these apps have access to as well. But I'll give a concrete example of that actually next, because I think that what you'll find is that the definition of these permissions goes far beyond these simple text and icon descriptions that you see here. So one example of this is location services. And we did see on the previous slide that both iOS and Android have an explicit means of moderating the permission for an app to access the location services provided by the phone. And what the location services are a software component that is provided by the operating system. This is a backend component, so it doesn't really have like a specific screen wherein you can see how the location services are working. But it's a service that the operating system provides to apps, provided that the permission is allowed, which enables that app to determine the location of the phone. But specifically, what location services refers to is the ability to determine the precise location of the phone using a variety of sensors. It allows the phone to determine its location using GPS or satellite systems, but it can also use nearby cell towers. Now, there are also ways of determining your location through other systems that are not necessarily explicitly part of the location services. One which has recently been amalgamated into that permission by the Android operating system developers, and which has also been amalgamated to some extent by the iOS developers, is the ability to determine your location based on other things that your phone consents around you. And specifically, we're referring to things like the presence of Wi-Fi access points and the presence of Bluetooth signals. Now, we'll go into a little bit more detail about what Bluetooth and what Wi-Fi access points, to some extent, can do a little bit later. But I want to impress that what this means is that the permissions, while they provide a best effort means for the operating system, again, via the developer, to determine what the app can get access to and what you consent to by allowing the operating system to enable that permission, there are still other ways of determining your location. Now, to be clear, the way that it works is when you actually allow this permission, the phone uses the sensors, it determines your location, and it makes that information readily available to the actual app itself. And the app cannot access this GPS receiver on the phone, nor can it use the cell tower service or the Wi-Fi access points in order to determine the location of the phone. But if a misinformed or enterprising or potentially malicious software developer wanted to determine your location, and they wanted to do this without your permission, well, it's certainly possible to either inadvertently or purposely develop software which can do this. And in fact, the reality is that based on cutting-edge research, there are many, many new ways of determining people's location using other sensors that are readily available on phones and other devices as well. This is simply the nature of technology, and this is one of the limitations of a so-called permission architecture. The permission architecture moderates access to the facilities of the phone as specified, so the intended facilities of your phone. But it's always possible, if you're clever enough, or if you find some way of working around the permission architecture, to potentially break this paradigm. Now, to be clear, the policy guidelines of all app stores explicitly prohibit doing things like inferring your location through other means. But there has been a lot of press in the past about how on many different mobile platforms, it has been possible to potentially track the location of people's phones through other means. Again, it's possible to do this even inadvertently. If I'm a very clever software developer and I really, really want to find out someone's location, then there are ways of doing it. But if you're going to be an ethical and responsible software developer, then the aim is to use the permission architecture, because that way we can at least have some level of assurance that the end user of the app actually consented to having their location tracked. Now, let's talk in a little bit more detail about Bluetooth. Bluetooth is not actually explicitly a location tracking technology. However, it can be used as such. Bluetooth is a communication technology, a short-range wireless communication technology. And there are many, many Bluetooth devices out there. Some examples are Bluetooth mice and keyboards. Smartwatches often communicate with a phone using Bluetooth, and you can also connect to your car using Bluetooth. There's an Android Auto application, which is a front-end application intended for your car that can then use the services provided by your phone as a backend. And there's also an Apple CarPlay app, which works in much the same way, but within the Apple ecosystem. However, there are many other forms of Bluetooth devices, and one example is a Bluetooth beacon. As you can see, Bluetooth beacons, they're inexpensive radio transmitters, and we're talking pennies. And what these devices are intended to do is to simply get stuck on a wall or stuck on a floor or stuck on a ceiling and to broadcast. And the way that one can track a location using Bluetooth is because each beacon has on it a unique signal, a unique address that is only broadcast by that one beacon. And because of the nature of Bluetooth, since it is so short range, only broadcasts in the vicinity of that beacon. So if I place a beacon in my local coffee shop, and then I take a moment to note the coordinates on Earth, the geolocation of that coffee shop, then I can be pretty well assured that if my phone detects the presence of that Bluetooth beacon within that coffee shop, that I'm probably at that coffee shop. Now, that's not to say that the technology is perfect or that there aren't ways of breaking this technology, either by jamming it or blocking it or otherwise. But generally speaking, these Bluetooth beacons are nowadays distributed everywhere, and most mobile operating systems actually use the presence of these beacons in order to help determine your location. And previously, these Bluetooth beacons could be used to determine your location without explicitly giving access to location services. However, it is important to note that the permissions architecture changes over time. And what the developer can access, and therefore what the user consents to, by the definition of a permission, also changes over time. And as updates come out to the mobile operating systems, these permissions continue to evolve, and new permissions can get added, and permissions can get amalgamated with one another, and also the permissions definitions themselves can change. So it's no longer the case that just by getting access to Bluetooth, which was not previously a permission that one actually had to give consent to, you could actually get access to the location. But that's no longer the case. However, as I pointed out earlier, it's always possible that by exploiting a potential weakness in the permissions architecture, a very clever or a very malicious or a very enterprising and uninformed software developer could inadvertently find ways of using the facilities of the device to either detect or infer things about it without using the permissions. And again, a clear example of that is location, but there's other things too.
Just to jump in for a second on the Bluetooth point.
Yes.
While you point out a number of ways that the data might be used in ways that may not have been intentionally intended originally,
yes.
I think it might also be important for folks listening to understand that there is a legitimate and valuable resource in using Bluetooth.
Oh, absolutely.
We see it used, I think, frequently in communications. I know iOS uses it often for things like AirDrop, so that you might actually be able to share pictures with somebody that is nearby. It can also be used, I think, a lot of times in stores. They may use it for amusement parks, I think, also use it for tracking patterns of movement, where maybe you're not actually trying to track individual users' locations, but maybe just to understand how areas are used.
Yes, that's absolutely true. And to be clear, there are many, many ways of legitimately using Bluetooth, and it's certainly not something to be scared of. As I said earlier, it's fundamentally a communications technology. But because you can do things like put beacons in areas, it's also possible to do things outside of its original intent. But the permissions architecture on mobile operating systems provides ways for ensuring that, at least for legitimate developers, that they are actually providing consent to access the location services. And so the issue here is that while cutting edge privacy and security researchers will often find ways of exploiting weaknesses in these permissions architecture, the nature of software is that it's always changing. So if a weakness such as this is found, it can get patched and it can get fixed. And the evolution of the permissions architecture can therefore ensure that things like Bluetooth location tracking can be used in a safe manner. And it is often used for very legitimate purposes. In fact, one very good example, as you mentioned, of people putting various Bluetooth beacons in different locations is that GPS technology is not perfect, and it often fails to work indoors. And by the same token, the cell tower-based location tracking is extremely, extremely coarse. And so while the cell tower-based location tracking might be able to get you, an approximate location, maybe plus or minus 100 meters of your actual location, which is certainly not good enough to determine if you're in a coffee shop or not, while the GPS, in the best of circumstances, might be able to get you an accurate location plus or minus 1 meter, the moment that you walk inside the coffee shop, or you start walking around a shopping mall, or anywhere else that has a roof or maybe tall buildings around you that happen to block the GPS signal, well, we've completely lost you. So by placing these beacons inside these locations, you can actually very accurately determine that that's where you are. And as a result, we can more accurately help people navigate. We can get them to the locations that they actually want to go. And businesses can also benefit from this because, as you mentioned, it gives them some ability to determine that there are people in their vicinity. And when they consent to sharing that information, that means that they can also potentially be given things like special offers and other things of that nature. So all of this tracking technology sort of feeds into a software ecosystem whereby not just apps on your phone, but also applications and backend services developed by others can use all of this data to actually provide value to end users. But the important thing, again, to note is that this ideally, based on law or otherwise, although I do not claim to be a legal expert, should happen based on people's consent. And that's why the developer guidelines do actually state explicitly that working around the permissions architecture in these mobile operating systems, well, that's likely to get you kicked off the App Store or to get your ability to put apps on the App Store revoked, potentially even permanently. And this does routinely happen on both the Apple App Store and also on the Google Play Store.
Thanks. I'll also jump in and say to anybody who has joined recently, if you have any questions, please feel free to put them into the chat in Zoom. While the audio is not available for participants, we are monitoring the chat, and I will feed your questions to the experts to get you answers. Thanks.
Okay. So at this time, I'm going to just give a slightly deeper dip into software components and software architecture. And what I'm going to do is I'm going to introduce the concept of an application programming interface, or an API. Now, many people have probably heard of APIs and maybe wondered exactly what they represent. And there's this rather complicated diagram in front of you. And what I'm going to do is I'm going to walk through this diagram to explain some fundamentals of software architecture. And in doing so, I'm going to describe with examples of exactly what an API is. So we've talked about hardware, we've talked about software, we've talked about source code. But what we haven't talked about is the way that software components can potentially interact with one another. Because software is based on building software on top of software on top of software. Software doesn't necessarily run all in one place. And so it would be a mistake to think that the application or app that's running on your phone is actually only just running on your phone. As I mentioned earlier, it's often the case that the front-end component of an app runs on your phone, but that a back-end component runs elsewhere. It might be running on a data center provided by Google Cloud Platform, or maybe by Amazon Web Services, or maybe by Microsoft Azure, or maybe I'm just a guy in a garage and I'm going to build my own server, put it in the corner, connect it to the internet, and that will provide the interface. So application programming interfaces are the interfaces that enable software components to utilize the services and features provided by other software components. And so it is the case that a front end talking to a back end will use the application programming interface provided by that back end in order to take advantage of the services that it provides. So how does that factor into this diagram that we're seeing here? Well, let me just get the pointer up for a moment. Can everybody see my pointer on the screen here? Right.
Yes,
so,
we can see it.
Thank you. So here in front of you, we see a very generic software blueprint, or a very generic software architecture. And the boxes and the lines connecting them, I'll go through to explain one by one. Let's start with tier 0. Now, what we have in front of us is what's called, to software engineers, a multi-tiered architecture. You can see that there's tier 0, tier 1, and tier 2. And each one of these tiers represents a collection of software components, each represented in the abstract by one of the boxes. And the lines that connect between the boxes represent the ways that these software components interact with one another. that interaction comes about as a result of an application programming interface. So, as I said, tier 0, we have a client application. A client can be a form of front end. That could be the front end.
I'm just going to jump in for a second. Sorry to interrupt you, but I think your pointer has disappeared. So I'm going to blame technology. I don't know if there's a different, there, it's back now.
Is it back now? Okay.
It's back now. I'm blaming technology for this one.
Well, software is hard to make right, you know? It's hard to make it run perfectly. And how software runs is one of the fundamental concepts of software architecture. So when we have a front-end application, that is often referred to as a client. But I'm referring to client in the abstract here. It is also true that a piece of software that is not intended for an end user to run on their phone can also act as a client. So for example, let's try to ground this particular diagram in an example of a bank application. So a good example of a client would be the actual app that you run on your phone in order to interact with the services provided by your bank. So you can do things like look at your account balance, you can do things like make a deposit, you can potentially do things like make a withdrawal, and so on and so forth, or even make transfers. Now, actually, it occurred to me that you probably can't make a withdrawal on your phone, but it's very easy to simply swap out the client that we're referring to as a phone app and talk about the client as an ATM. And the software running on that ATM can also be a client. So you can see here, when I refer to the term client, I'm talking about it in the abstract. What we're talking about is some form of front end that a user can interact with that can enable them to press the buttons and move the dials and type in the numbers, that gives them the access to interact with the features provided by the service. Now, the client exists at tier 0, and as it crosses into tier 1, it needs to make a request to an application server that's probably being operated by the bank. It's very likely that the bank wrote the software for the application server, because this application server serves, hence the name server, the different software services and features that are needed by the client in order to then, as a result, serve the user. So when the front end offers features like being able to check your balance and make a deposit and so on, that then means implicitly that the application server is going to be providing those features to the client. And so how does this relate to an application programming interface? Well, some software developer needs to actually write the code that gets that client application to talk to the application server to then do the thing that the user will then tell it to do. And so the specification of what these services are and how you interact with them, which is also known as a protocol, things such as the rate at which you can ask it to do something, or the kinds of things that you're allowed to do, and so on and so forth, those are all specified by an application programming interface. And APIs aren't necessarily written in one particular programming language. There are many, many different languages and standards and ways of specifying an application programming interface. So fundamentally, it's simply an abstraction. It's a way of thinking about the collection of services and how you talk to them and what they provide. So why the tiers? Well, the difference between tier 0 and tier 1 can often communicate where the actual processing and computation and so on is occurring. So I've already mentioned that the client is very likely running on someone's phone, or it might be running on the actual ATM terminal that you're interacting with, or it might be running on your desktop computer, or it might actually be referring to your web browser. Doesn't really matter. The client is abstract. And just like tier 0, tier 1 can potentially be operating anywhere too. But the kinds of places that an application server runs, because it's on the back end as opposed to the front end client, the application server, or tier 1, generally tends to run in data centers. So as I mentioned earlier, that could be provided by anyone. And it could be physically located anywhere, because the internet enables the requests and the responses that the client sends to the application server to be transmitted anywhere, and really at any time. So the application server then brokers the communication between even more backend components. So what we've talked about is sort of the business logic. That's provided by the application server. The services and features that the front-end application then offers to the user. But that can't run all by itself. If we're a bank, we certainly need to be able to keep track of our banking records. And so generally, that will happen on another tier, which could yet again be running somewhere else in a different data center, perhaps at a secure location, since we need to be extra careful about things like banking records. And so we need to take extra care to ensure that the API that, in this case, the data server provides for the application server is extra secure, and that it provides the sort of lower level features that are necessary in order to provide the functionality that the application server in turn provides to the client. So these are likely to be more sort of low level instructions. What the client sees are high level instructions, things like, I want to make a deposit. And so what that means to the bank's backend isn't necessarily something as simple as, okay, just make the deposit. Often what that actually entails is a number of other additional low-level steps that are abstracted away from the end user and that they don't necessarily see happening under the hood, so to speak. That's also why we call it the backend. So one example, when we probably need to make a withdrawal, for instance, is that we need to do things such as checking that the balance for the withdrawal that you've requested is adequate, and that we've got the right account, and that there aren't restrictions on your account, and so on and so on and so on, until we've got all of the different functions that the software on the back end needs to do in order to do that simple, potentially one-click action that the user requested on their client. And so in this case, in Tier 2, these are all operations that generally have to do with the data. And so we see that there's the data server, which is another piece of software that then interacts with this hockey puck, which is a traditional, or hockey puck or cylinder, or which is a traditional notation for a database. Now, when we say DBMS, we're talking about the database management system. Why? Isn't that the same thing as a database? Not quite. The database management system is a different piece of software that then interacts with the database. The database itself is just the medium of storing the data, but there still needs to be provided some form of programmatic interface to actually interact with that database. And so now you can see we're kind of peeling apart the layers in order to expose all of the different APIs that are part and parcel of a software system. So there's an API between Tier 0 and Tier 1. There's an API between Tier 1 and Tier 2. And then even within Tier 2, there could potentially be multiple APIs for the data server to interact with the database management system. And then for the database management system to interact with the database within. And then, of course, what's even further abstracted away, which we can basically do ad infinitum until we get down to those little binary instructions running on the hardware, is that the database will talk to the hard drives on the server in order to tell it, you know, store these bits and bytes of data at this location because that represents this account, and so on and so on and so on. And so what these APIs provide you with are abstractions that take away all of the complexity of having to think about all of the underlying complexity that you're interacting with when you're executing higher and higher and higher level instructions. And as we build and build and build upon these layers of software, we end up with complicated software systems. And so when we develop diagrams like the one that we see here, blueprints, in order to describe a very generic software system, in fact, this type of multi-tiered architecture with these types of 4 components describes probably roughly about 90% of software systems out there at the moment. But when we develop diagrams such as this, it enables us to reason piece by piece and component by component about all the bits and pieces that make up the system. And so in doing so, it enables us to do more complex reasoning. And it enables us to think about things, not just what the system should do, but how it should do it, how fast it should do it, what types of components and what operating systems we want them to be running on, such that we can have things interoperate with one another. It enables us to think about the types of services and features that these different components need to offer to one another in order to perform their jobs. And then when we think about those features, and when we think about those functions, we can then also think about the data that needs to be moved around and where that data needs to be processed in order to give us the result that we're thinking about. So all of these complicated decisions are inherent in what applications developers actually do when they write software. But you can see that because when I'm a front-end developer and I'm simply developing an app that's intended to interact with a backend that's only offering a limited subset of features, some of which may not be documented to the level of detail that allows me to reason about all of the further underlying things that are happening, that's an easy opportunity for mistakes to be made. And they often happen. So to mitigate this, developers put together documentation, and they put together detailed APIs in order to ensure that the people using the APIs can fully understand the consequences of the design decisions that they're making by utilizing the different functions provided by APIs at all the different components of the system.
Daniel, can you speak to where in the architecture mobile identifiers will sit?
Well, it's possible for these mobile identifiers to kind of move their way through any of the pieces of this architecture. It really just simply depends on how it's been designed. So generally speaking, as we described, the client runs on the mobile device. So it's most likely that the identifier will originate on the client. And then if it's transmitted, because that's what the application developer has written, then it can be transmitted to this application server, which might do nothing with it. Or it might send it out to the data server, which then might in turn store it somewhere. It's often very difficult to reason about where data goes as it transitions between system boundaries or as it transitions between APIs. Because the problem is, I, as the application developer, am developing most likely just the client. Or I might just be developing only what's running on the application server. And perhaps the company that I work for, even though we control and own tier 1 and tier 2 of the system, I might not be developing all of what's in tier 1. Maybe we've outsourced part of it, or maybe we've outsourced all of it, or maybe we've outsourced part or all of tier 2. And the nature of software today is that this outsourcing and that this data sharing and movement and the usage of off-the-shelf software components that are provided by a variety of developers is very much ubiquitous, and it's very much commonplace, and as a matter of necessity, because software systems are so complicated that if I had to develop every single one of these components just so that I could make a very simple client application, it would take me years and hundreds of developers and potentially hundreds of thousands of dollars in order to even develop that to begin with. And yet, the application that's running as the client even still can often be an expensive proposition based on how complex it is, or based on other things, such as how fast it needs to be, or how much scrutiny it needs to undergo in testing to make sure that it really does do all of the things that we think that it does, which can often be lost, because software isn't something that you can just simply pick up in your hand and inspect for quality. It often takes expertise and time and effort and understanding to pore over its contents. And if the documentation is inadequate, or if the code is messy and complicated and impenetrable, then mistakes can be made. And so one example of a common mistake that can occur is inadvertently allowing things like individual identifiers to move off the device, the client, when they don't need to, and to then pervade the entire system, or to even be recorded when they don't need to. I'm sure that many policymakers are familiar with terminology like data minimization, where essentially you only keep the stuff that you really need to do the thing that you said that you were going to do. But the problem with the nature of software is that it's often very difficult to reason about everything that it is that you're actually doing, because sometimes it's hard or even impossible to pierce the veil or to lift the hood and to go into the back end and to see exactly what it is that's going on there. Often the best that we can do is simply guesstimate what's happening based on what's documented. And that documentation could be incorrect or out of date, and so on and so forth. And so it's very challenging.
Thanks. We've received a couple questions in the chat. I'll just remind folks that if you have a question, please feel free to type it into the chat, and we will get it up in front of your experts to answer. The first question we have is related to consent management, and the question says, when consent is given at installation, when installing an app, as mentioned earlier for certain permissions, how and where and by whom or which party are consent records managed? The thought is around accountability and compliance.
Yes, so that's a very, very good question. And the answer is, it depends. The problem is that the actual mechanism by which an app developer or their company are recording the consent that they have to do certain actions is completely incumbent upon them to develop and to implement and to ensure the correctness of. And so the problem with that is that consent is only implicitly given as a result of installing the app for those permissions that cannot be moderated after the fact, and that are only consented to as a result of actually installing the app. So the issue here is that when you give this consent, if you wish to revoke the consent, the only means by which you have to do that is to simply uninstall the app. And as far as I know, unless the app developer has gone through the pains to make sure that they know that you have uninstalled the app, and therefore also implemented some means of perhaps deleting data or recording that consent was revoked, or really anything else for that matter, there simply does not exist any mechanism for managing that consent. So when I say consent in this case, I don't wish to imply any particular legal definition. As I said, I'm not a legal expert, but what I can say is that when you are actually asked, particularly in Android, to give permission to give the app access to these permissions when you're installing, that is really your only way of consenting or not consenting to it. But if you don't wish to consent, you simply don't install the app. Now, for the other permissions, of course, it's the same story, except you do have control after the fact. So if I wish to revoke the permission for the app to get access to the camera, then when I do so by opening up the permissions management screen on iOS or on Android, which again is another app, it's just simply provided by the operating system as opposed to the app developer who I'm trying to either give permission to or not. I open that app up and I can enable or disable that permission. And that is how the operating system keeps a record of me giving that permission or giving that consent. But that should not imply necessarily that the app developer has gone through any effort to actually record that that permission has taken place. Often it's the case in most applications that the functionality that depends on having access to these various facilities of the device, when that permission is not given, those facilities just simply cease to function. But there's no other record, no other knowledge on behalf of the app developer that that permission was given or not. Again, the app developer has to program that themselves.
Thanks, Daniel. We've received a couple other questions in the chat that I'll summarize, but I believe that they may actually be answered best by going more in depth into part 2 with Ferris. So the questions are around the app permissioning and whether apps generally ask for permissions that are absolutely necessary for operations, or are we seeing permissions to access data that's not required for functionality, but maybe a nice to have for additional data gathering like body sensors?
Absolutely.
And then the next question would be around low code, no code platforms, and how do they complicate in terms of the control of personal data in systems? And
that's an excellent question.
I suspect those might be answered with some of the upcoming content, but.
Well, I'd like to address the first question, if I may. So, as was mentioned in the introduction, one of the many research projects that I've worked on is in mobile app compliance. And one thing that we did is we analyzed all of the free apps on the Google Play Store, and we attempted to determine, based on analyzing their privacy policy and based on analyzing the source code of the applications, whether or not they appeared to align with one another. And so, as we know, the privacy policies of these apps make disclosures about what the apps are supposed to do and what data they collect and what they do with it. But the source code, while it is legally bound, and again, I'm not a legal expert, but while it's legally bound by that privacy policy, it's very easy, as I've described earlier, to make mistakes, either inadvertently or maliciously. Now, the issue here is that the software components that make up a complex software system, sometimes we don't get the ability to introspect into all of them. And so when I use a third-party library that's providing me with a specific set of functionality that my app needs in order to do what it is that it does, sometimes that third-party functionality can include the usage and collection of data that I, as the original developer of the original app, wasn't aware of, and therefore may not have even made a disclosure about. And this happens incredibly often because these third-party libraries are intended to provide an enormous amount of functionality. This functionality can range anywhere from, as mentioned earlier, making body sensors work in order to determine, your level of fitness activity and, whether you're moving enough and things of that sort. And they can also provide other functionality such as, putting advertisements in my app. All functionality that I, as the original developer, don't want to have to undertake the cost and effort of developing. But as a consequence of depending on that and incorporating that into my app, I may inadvertently or even be aware of the fact that these third-party libraries are actually collecting additional data that I don't need or that I didn't intend to collect. And so this can result in misalignments between the privacy policies of apps and the actual app's behavior. And it's quite commonplace.
Thank you for that. I want to make sure you're still going to stick around with us through Ferris's portion and be available for any additional questions that might come in at the very end of the session.
It would be my pleasure.
Excellent. Thank you so much. And with that, I think, can you pass the control over to Ferris?
Yes.
All right. Hi, everyone. This is Ferris Alraie. I'm the Chief Information Security Officer at Mattel. I also have the privilege to manage the privacy office as well, too. I'm located in El Segundo, California, and that's in the LA area. So I'm so excited to talk to you today about a couple of topics here that I think it's interesting, it is required, it is sometimes not necessary. There's a lot of confusion around it. And I'm also going to carry some of the items that Daniel touched on. That will be really good because then I don't personally, and Daniel, overwhelm you with all that information that was just thrown at you. So the areas that I want to touch on today is mobile identifiers and designing an app with privacy and security in mind, and that's from the get-go. Basically, that includes sharing data with third parties, ad libraries, SDKs, and also perhaps we'll touch on the secure software development lifecycle and how do you then do all the checks and balances for these systems when they're built. Just to reiterate on what Daniel said is, a lot of these systems are complex and a lot of them are built by different components from different areas. And we'll touch on that a little bit when we get to SDK. But before we do that, let's talk about a little bit about mobile device identifiers. What is a mobile device identifier? Why was it created? What is this gigantic number that I look at and I see? Why do developers end up using it? Let's take in one example, the universal device identifier that you would see in your iOS or your mobile device, which is your iPhone. Obviously, Android have a similar one, but they would name it differently. But let's talk today about a little bit the mobile one, the iOS one. The universal device identifier is 40 characters long. It actually was generated to be a random identifier that belongs to that device. It wasn't meant to be used for any other reasons. It was created as a token that lives with the device, so then the device is identified. Having that token on its own, if it's written somewhere, it will mean nothing. It will equal to nothing. So they rely on things like the identifier. Well, how does the identifier becomes the tracking mechanism? Is actually the add to it other elements that will help in that, such as the actual real name of the user, the username, the passwords, the location, and other data. Once you put all these data together with the identifier, that becomes actually a problem. And that creates the situation where now we know who that person that using that phone at that time for that identifier. There was a lawsuit in regard to actually the identifier itself on Apple. That lawsuit was dismissed, but Apple took the safe route on that. And on October 2011, by the release of iOS 5, Apple stated that anybody that would use the UDID, they will actually be rejected from the Apple Store. So Apple starts shutting the process of using the identifier as a mechanism to do that. So obviously, the developers started looking into other mechanisms. What are these other mechanisms? Let's just talk about them a little bit. One of them is the media access control address, which is basically the MAC address. This is literally is a unique identifier for your network communication device on that mobile device that tells how are you connecting to what network and what sort of communication you're going to be doing at what levels. The other one is the advertising identifier. Now, I'm going to leave that advertising identifier a little bit to the end of it because I personally think from seeing it in real life, that's the biggest problematic ones between UDID or the MAC. For the UDID, as I said, Apple rejects it now when they put on the Apple Store. A lot of systems that we use, they actually get flagged, so they get turned off. There is no reason for a developer to use it. Absolutely, that's from real life example. But you still see behaviors where developers will use it, and it's extremely not helpful. Well, what about the media access control? Can that be helpful? In some scenarios, yes. If your app pertaining to a network devices and helping you with that. Other than that, there are reasons to really utilize the MAC address. There's also weaknesses where I can actually replicate the MAC address. So I can clone the MAC address. And so then I can deceive the system from identifying, is it me or is it someone else? So it plays both ways too as well. Let's talk a little bit about the advertising identifier. That's the one that I think is a little bit of a problem. It was introduced in the iOS 6. And obviously, probably the reason for that is to remedy a little bit the universal identifier blockage that Apple put in place. So they said, okay, well, hold on a minute. If we need to create an app that does advertisement, then we need some sort of things to tell us what we can do and can't do. The advertising ID, even though you have the option to actually set the limit ad tracking, we'll see that in the next slides. What that ID allow you to do, allow you actually to see a lot of data on that user. Information such as keyboard language, OS version type, location, mobile carriers, you name it. Well, what's the reason for seeing all these things? Obviously is to do a targeted advertisement, or to do geolocation advertisement. Means if you're located in Europe, you might receive different advertisements that say you are located in the US, and so on. So these are the differences that this actual identifier will help folks to, or developers to utilize. Now, in my personal experience, the advertising identifier, really, it's not necessary unless you're building an advertising app, which is uniquely, you need to be in that business to do so. Other areas of the mobile development world may not need to use it. Having said that, though, there is a flag that you can turn on called limited ad tracking. Now, on the Android, is a little bit different, and the reason it's a little bit different is it's what Daniel touched on, in the sense that you have two distinct platforms, which is the iOS and the Android. We're built differently. They have different mindset. Even updating these devices are done differently. One that is constantly updated, it is controlled because it almost looks like a closed loop by the Apple developers, where the Android, you can potentially still live on older devices, which might carry some of these weaknesses, and they did not get updated as fast as possible.
Can I jump in for a second on the mobile IDs?
Please do.
It looks like these all are mobile IDs that originate from the specific mobile device. We have a question that came in around other identifiers like an SSID, which was recently mentioned in an FTC complaint and settlement. Can you speak to where that might originate and how it factors into mobile device IDs?
Absolutely. So the SSID is really not in the mobile device itself. The SSIDs are actually, these are your Wi-Fi identifiers. And so let's say you're in a Starbucks and you connect to a Wi-Fi. That's your SSID that comes out of it, and that gets actually obviously it will be in your phone. You'll see it. It will record itself on the phone, but obviously it is not something that a developer will decide to turn on. It is something that the OS will help you, so you can connect to different networks across the spectrum. Is there more specific to that question that the person would like me to touch on?
Are these mobile identifiers always automatically collected?
So it depends. Again, that goes back into what the developers will actually intend to do. For example, and let's simplify it a little bit. When you are starting to develop an app using, say, Xcode, you open up the Xcode and you start coding. There is a file called the plist file. That plist file contains the permissions for each one of these identifiers. You can turn around and say, and turn it off. Say no, basically turn it to no versus yes, right? A lot of developers may tend to neglect that part and then leave it on. In previous versions of the iOS, for example, it was turned on by default. In the newer versions, they decided to turn them off by default. Obviously, that does not stop the developer from going back and turning them on themselves.
So would it be fair to say that while there are identifiers generated by devices, whether it be the mobile device or access points around where a mobile device is at a time, the information can be transmitted, but it may not always be collected and stored or used?
Absolutely, that is so correct. So let's touch back a little bit on that identifier. So for example, the universal device identifier, it's baked into the OS. It's actually built up by Apple when they build the OS, the operating system. They use it so they actually can identify that phone. It's a random token that identifies that phone. So happen to be that you go to their store and give them your phone, then they actually know, hold on, that phone was manufactured at that time. That's why they use that token, right? What the developers did is they purposed that identifier for other means, which is basically, if I use it with, say, person information on user ID and passwords, I now may create myself a session that I can use and mimic, right? Which is the wrong thing to do. But unfortunately, some of us as developers, they would do that. So not that you can say, I'm gonna turn off the device identifier from the Apple operating system, which you can do that, it's there. But as a developer, when I'm building the app, I select if I wanna use the identifier or not. I'll give you an example why would someone use the identifier. If I'm building an application that will do, or an SDK, which we'll talk about that in a minute, and I don't wanna speed up the process here. If I wanna build a hash value, basically hash value, what that means, and we'll touch on that a little bit, is it makes it unreadable. I need a unique number to be used, like a token or a random number. I might use the identifier to do that. But that does not mean I'm actually taking that information and passing it over to the backend and storing it at the backend. The reason I'm using that random identifier, because that value will be different on each device. It will be separately different, so a hacker will have harder time to break it. That's the difference. So that's a good case of using an identifier. A bad case of using an identifier, using it instead of a session ID to actually manage the person information. Any other question, or I can move to the next slide?
We did get one other question, and it's around fingerprinting. And the question is whether fingerprinting or identifying a device based on a lot of unique data taken from the phone is also possible on smartphones.
Absolutely. So fingerprinting, it's an interesting topic. I've touched on that. I actually worked on that myself when I was securing the Apple Pay. Back in my days in a different far land. The thumbprint on, say, an Apple device or Android device, that information is very strictly controlled by the operating system for a user to access. But what Android and iOS does is they actually expose some of these, how should I say, it's not really identifiers, but flags. You can think of them as flags that says, do you want to use a fingerprint for an authentication mechanism? What that means is, do you want to use it as a way to say that this is the person that that person is claiming to be, right? So for example, if I want to say, if I give you a username and a password and you type it every time, and you're tired of doing that, I might use the thumbprint for me to say, I'm going to utilize that instead of the username and password. But my app will not be able, say, to scan the OS to be able to grab out of it the patterns of your fingerprint, right? We got to be careful in kind of going down that rabbit hole where can I actually access the patterns of your fingerprint? That's actually strictly controlled by the OS and by the operating system. And actually, there are secure elements on that OS, on the device that actually stores that sensitive information. Other ones, basically, when you use your Apple Pay, the token that's created based on your credit card is actually stored there as well in the secure element. So they are not accessible to developers. But what they allow you to do is use it as a second factor or as actually authentication to another system.
Thanks. And one other question, can you describe or explain what the IMEI number is and whether or not that's available to developers? So that number is also, again, it's an identifier for the model that was built for that phone, right? So obviously, if you look at different models of the phone between the, say, for example, a iPhone 6 to iPhone 7, 8, the S type, the X type, right? That value is actually used more by the telecommunication companies to allow the communication to actually register the phone itself. That's the only way they can allow the SIM on your phone to communicate with your actual phone using that identifier. Can someone access that identifier? In
a real life scenario, and I'm going to try to refrain from kind of walking into another discussion about jailbroken devices, right? But I'll touch on that just a little. It's not part of this discussion, but I'll touch on it just a little so I can explain the differences. If the device is basically strictly purchased device that you use, and obviously needs to register with a company such as Verizon or AT&T, they would use that value to connect it with your actual SIM card, so then you get the service you need. Now, previously, before previous lawsuits, that device used to be locked up to that Verizon provider using that ID. Can applications that someone built access that? Not really. The OS will not allow you to. Can someone access it through a jailbroken device? Absolutely. What jailbroken device means, I actually now exposed the internal working of the operating system. So then I can access IDs in that manner. Obviously, it is not recommended that someone jailbreak their device. If someone is doing it, then they're willingly doing that, so they know they're actually walking into a really bad scenario. That phone can be taken over easily. The reason they would do that is because I want to unlock my phone so I can actually go with any other provider. And so that's really where it becomes a little bit of a whole different discussion that I want to refrain from going into at the moment. Otherwise, we'll chew up another 2 hours.
Thanks. Out of curiosity, Daniel, did you have something to add on the fingerprinting point?
Actually, yes. So I just wanted to very briefly distinguish between using the human's fingerprint as in like a way of biometrics authentication and the concept of fingerprinting in general, which in sort of the software engineering community is often referred to as using a bunch of sort of disparate information in order to uniquely identify someone or their device, which of course, you know, a human fingerprint is a fingerprint in the strictest sense. But one can easily determine that a particular phone is a particular phone using an amalgam of a whole pile of different information as well. So the idea here is that yes, it is possible to individually fingerprint smartphones. It's also possible to fingerprint web browsers, and by virtue of that, it's also possible to fingerprint individual web browsers on smartphones. And the way that this is done is by just simply collecting any information that can be collected. And then by amalgamating that information together, one can create sort of a statistical picture about the likelihood that the device that you're looking at is the device that you think it is. And you can narrow down the possibilities about what device it is that you're referring to, the more information that you collect. And so some types of sensors and some types of identifiers make it super obvious. If I know what your UDID number is, or if I know what your MAC address is, because these are unique, I instantly know who you are, and therefore I've fingerprinted you. But if I don't get access to this, I can still fingerprint you using a wide variety of techniques, and there are new techniques for doing this emerging every day. These can be even things as simple as determining the touch patterns of how you actually use the buttons on the smartphone display. If an app records this in detail and shares this with an application developer, if the application developer shares this, this information can actually be used to infer the unique pattern by which you and only you actually interact with your smartphone. We can look at the accelerometers to determine how you hold the smartphone, how you walk with the smartphone. All of these sensors, when the data can be, especially when the data can be combined, can be used to create a unique fingerprint and determine that that device is you. Now, there's both positives and negatives to this. The positives to this is that it's an ongoing field of research, and we can use this to create new forms of biometrics such that we can safely identify you and use that to determine that the person holding the smartphone, for example, might be the person we actually think it is. That'll be in the future. We're not quite there yet. But that can also be used maliciously for the same reasons. And so we have to be very, very careful about that, because again, that information, while seemingly innocent, such as just detecting where somebody might be tapping on the screen, Could be used to determine if the, for example, Frontend has bugs in it. Is the screen content what we think it is? How are people using the app? Are they using this feature and not that feature? But taken into a different context, it can be used for fingerprinting.
And I'll just jump in with a bit of a spoiler alert. There will be another masterclass session in the fall that will touch on biometrics. And I think that folks who want to dive deep into some of this, the biometrics and the fingerprinting and all might be interested in listening in on that as well. I'll also note that in my experience, the ability to do device fingerprinting within a specific app is a little more complicated and maybe a little less reliable just due to the closed ecosystem there and the difference in the access to the data points. But with that, I'll let you continue on with your presentation, Ferris.
Awesome, thank you. All right, so let's talk a little bit about the limited ad tracking. Again, going back to that advertisement tracking ID that was reintroduced or introduced, I shouldn't say reintroduced, introduced in iOS 6, and therefore it continued on. Obviously, there was an uproar against Apple and Android and everyone else about, so now that you created that ad tracking ID, which is the identifier for advertising, well, hold on a minute, you got to give me the option to limit what I can share or can't share. So that therefore, if an app is actually producing content to be a very specific advertising content to myself, I would like to limit it. Having said that though, once you turn on the limited tracking features, it may omit some of that information such as where you are, geolocations or other information, but it does not actually bring it back to zero. That limited ad tracking will not make it zero. It's not a flag that says, I do not want advertisements. I just want to make that clear to everyone. It is more of limit what am I sharing with that third party for them to actually advertise to me directly. That's really the differences that I want to really touch on and compare in a sense. Now, can the developers access that identifier? The answer is absolutely yes. Can they turn it on? Yes. Would you get prompted that is being turned on? Again, that goes back to a topic that Daniel was touching on, which is you are implicitly and explicitly agreeing that you are actually okay with yourself being targeted advertised. How's that happen? Either when you're going to the App Store and downloading the app, you're just agreeing right there that you want to download and install it and have it on your phone, or by getting a push notification, which is really that square box that you would get in front of the application that says your app is tracking your location, or your app is tracking X, or your app's tracking Y. And then you actually don't have the option to say go set limited ad tracking. That would be actually something nice maybe to be introduced, and hopefully I can, through my work, see if I can communicate that with companies such as Apple and others. But it should be a toggle. In my opinion, there should be a toggle on that controller that opens, which is really the push notification that says, yes, I want to allow it, or I want to give it a limited tracking. If I do that, it's better, where now it's hidden in one of the controls, so I really have to jump through screens on my iPhone to get to it, so then I can set the limited tracking. So that's something I just wanted to touch on a little bit, because I think it's interesting. I think it's one of the ones that we should focus more on versus actually focusing on the device identifier or the Mac, because as I said, there are now controls where Apple won't even allow you to produce that and put it on the App Store, or even there are systems which we'll touch on in the secure software development lifecycle, where we track this and how we make developers responsible from not being able to do things from that nature. All right, so let's talk a little bit about the concept of encryption and hashing identifiers. What is the concept? Let's talk a little bit about the concept itself of encryption and hashing. If we want to simplify how we look at hashing versus encryption, it's very simple. Hashing, if you take a value, let's say my name, and you hash it, you should not be able to revert that value back. That's the concept of hashing. It's very simple. I take the value, I hash it, I get a random number. That random number should not be able to be reverted back to my name. Where in encryption, the goal is I encrypt the value, which is say my name, and then if I wanted to use it again, I decrypt it. So therefore, one, you can revert the value back, one, you cannot revert the value back. But what happened in hashing is how does that gigantic number it gets generated? What's the difference between MD5 hashing and SHA-1 and raw version and all these words that you hear out there? And somebody tells you, well, hold on a minute, MD5 is broken, right? You hear that sentence is somewhere out there in the ether all the time when you're listening to hashing. So hashing is primarily used, the focus of hashing is primarily used for password protection. What that means is once you enter your password on the screen, the server should not actually, the backend, as was Daniel mentioning, should not see that value. So if you store that value encrypted, then there's a possibility that I can decrypt that value and use it. But if you store it in hashed value, then there is no possibility for me to revert back your password. But then if you enter your password, how do they know that this is your password? And the idea is you hash that value again and again using the same routine in your software, and then do a hash comparison. Once you do the hash comparison, then you know that this is the person that actually entered that following value for the password. Well, what's an MD5, SHA-1, and raw version? Let's just talk about MD5 and SHA-1 so I don't get into other areas and confuse everyone. Basically, an MD5 and a SHA-1, they're the strength of the hashing mechanism to actually generate that large number. Now, a lot of times you don't just do the hashing, you actually add unique and random values into that hash value, so it becomes even more complex. For example, the iPhone, what it does is when it's creating a hash value of an identifier, it uses three things. It uses the hashing mechanism, which is in this case would be SHA-1. It depends because MD5, as I said, it's a bit weaker. Then it uses a salt. Then salt basically a random value that gets put in place. And then it uses something called iterations. What it means iterations is you're rehashing that value 20,000 times. And the idea is that you don't want someone to be able to break that hashing value. How do you break a hashing value? You have something called rainbow tables, which is dictionaries that actually compares values and returns it back. So if your value of hashing is very simple, like let's say if you take the letter A, the uppercase of letter A, let's say for example, and you hash it, that's a 4 digits there that you would see. It's probably like 2 alpha values and 2 numbers. And then you compare and go on. Now with the skills and the capabilities of our devices today, such as the laptops and servers, they can do that computation in a very, very fast pace. So they can actually revert that value back. So that's why the MD5 is broken. And that's why everybody's upgrading to the SHA-1 from that scenario. Now, what is the encryption? Encryption is really taking a value that you care about and then you encrypt it. And how do you encrypt it? You use a encryption key. That encryption key is a large sum number that you use to encrypt that value. The problem with that is where do you store that key so then you can always call it out back again to use it again so you can encrypt. A simple scenario in real life that you use so you can compare with that is the key to your door at your house. Obviously, if you locked yourself out, there is someone that you can call into your house and they'll come in and they'll unlock your door for you, or they can rekey your door for you. Well, what do they have? Well, they have a master key. That master key is the key encryption key, which then derive a key that you're able then to encrypt those values. Google and Apple uses it in a different manner, right, where they actually either hash a value or encrypt a value in different scenarios for different usage. Similarly, the developers in the development communities would do the same thing too. For example, the session that's moving between systems to identify that this person is the person logged in, they might use either a hashed value or encrypted value, as I touched on a little bit about the password mechanism versus the actual, say, name of a person, where it should be encrypted versus the password should be hashed. Any question on that, or I can move forward?
I think we're good. Keep going.
All right, excellent. All right, so let's touch a little bit on something called software development kits, which is short for SDK. You heard already from Daniel about the APIs. Well, what's this SDK? Why is there too many acronyms? And why the development world is confused on their own, right? It is not. So what it is, and Daniel alluded to that a little bit, is we're building complex systems. These complex systems cannot be developed by a single team. Things like, if I want to do encryption, do I have the skill set on my community of developers within my office, let's say, or within a university or anywhere else that can do this, right? Perhaps not, but perhaps there's another organization who specializes in encryption. So then therefore they will create an SDK, which is a software development kit. It's set sort of libraries, and that you pick up and you install into your app. What do you mean by installing it? Is you take it as a developer and then you start exposing the functionalities of that development kit and you write your code against it. So for example, if we say get a SDK that do hashing, then I'll pass it, for example, the word street. It will hash that value and give me that value back, the hash value. So I don't have to write that part. Now I can focus on writing, how can I present that value to the screen? So that saved me a lot of time. That actually made me not write something that I'm not familiar with, which I make more mistakes. So the idea is novel. The idea is good, right? Obviously, we'll touch on that a little bit in the third-party SDKs is some of these SDKs are written by anybody on a, say, platform such as GitHub or Bitbucket. Some of them are written by organizations such as Facebook, such as cloud storage like Amazon, and so on, in different areas. And I'll touch on some of these a little bit too. There are ones, and this is a recent an example, where there was an attack called zipper attack. Well, what's a zipper attack? There is an SDK that does for you it zips a file and it unzips a file. So why would a developer use that? They use it in an applications where you actually upload your pictures to. So when you upload a picture or a file, your file is very large. So what they'll do is they will use the zip mechanism to shrink the file. Therefore, it is faster to transfer to the backend and be stored. And if they want you, and if you want to see that file again, they will unzip it. And then they will expand that file, and then you can see the file. Well, the developer didn't write all that. They don't sit there and write, let me zip and unzip and rezip and unzip again. What they do is they use an SDK. Unfortunately, that SDK was susceptible to an attack where it changes the values in the actual zipping, where therefore it exposes your data, right? So that is kind of the good and bad of SDK. The good part is it saves time. It saves costs. It saves the developers from making mistakes because they're not expert in these areas. They could be expert in different areas, but at the same time is, like any other developers, mistakes could happen in the SDKs where it actually exposes things. Another example too is there was a recent article, it's not so recent, but it's in Wall Street Journal, where it talks about 11 mobile applications that's sending data to Facebook. Obviously, the author wrote it without kind of knowing or doing a little bit of investigation work on what the issue was versus stating the fact that Facebook somehow was grabbing that data. Obviously, I'm not supporting Facebook or I'm part of Facebook. I just want to make that clear. But I'm more of, I like to investigate and figure out really what went wrong so we can make things better. That SDK that Facebook provides is a social integrating SDK. Actually, they have documentations online of what values, what identifiers you need to set to actually follow the privacy regulation and requirements, right? Now, you can debate how good or bad it is, and that could be a different topic. I'm more than happy to take it on, but at the moment, I don't want to touch on it in details.
No, thanks, Ferris. Just to jump in there, I think that the example that you cite with Facebook being called out for receiving certain data, I think that's an excellent example speaking to the nature of the data flows and the ability of each individual entity in the process having the ability to independently decide what data they might collect and use and pass back and forth. And the requirement that there be, or the need for individual responsibility in the treatment of the data that you might receive. So an SDK is developed by an individual or another entity and can be incorporated into an app. And by nature of the incorporation in that app, it can then also receive the same information that the app has access to. So it's an excellent example, I think, of the complexity of the ecosystem and how so many different parties have to work together responsibly in the treatment of the data.
Yeah, absolutely. Absolutely. Well said on that. And that's exactly what I'm alluding to, is really kind of the responsibility falls on everybody. The developers, because they have the rights to turn off things and not allow the SDK to see it, as well as the SDK to start to clean up their act and start removing some things that does not need to be there, and so on. So there are different mechanisms. Another simple example, the cloud storage, Amazon S3 buckets. What that is really, it's a database in a cloud. There is a mechanism to make that database publicly available. There was an article the other day that someone was able to download data from every S3 bucket out there. Well, whose fault is it? Is it Amazon that allowed that flag to be turned on in their values, or is that the developer's fault? It's not so much that. I wouldn't look at it from a fault perspective. I would look at it same thing like we talked about in the Facebook, is the responsibility of doing the right due diligence, focusing on the right elements, turning off, having governing body over it that figures out what's going on and give right and responsibilities on what part, where does this lie. So that's really kind of what the entail here about it. But just to reiterate, an SDK is really a piece of code that you basically borrow from a different entity that then you put into your application, so it helps you do extra work for you, such as processing some sort of data or processing some sort of number crunching in order for you to focus on what really matters when you're building your application. That's really the novel part of it. Based on that, I'll move on to the next screen. So let's talk a little bit about, well, what is the designing privacy and security in apps from the get-go, from the beginning? Obviously, the community has a responsibility of how we are about to do this and how should we do this. That include actually every organization out there that produce piece of software. And this is something that has been developed back in the early 2000s. It is not uniquely new, but what makes it new is how you actually implement it in each organization. And I've been advocating for this for so long. I like to see this actually embedded in a lot of organizations out there, the small, the big, the medium, and the large. And I think it is actually beneficial for the organization, because some organization might see it as a burdensome on them. So let's talk a little bit about what this is mean. Like, what are these boxes? What do they do? And what are they about? Let's start with privacy impact assessments. Privacy impact assessment is a great way of identifying the data elements that you're actually looking at and working with, that then allow you to create a data inventory or audit, which is you see in the box where it says develop. So if you notice, they're kind of all linked in to each other to help each other succeed. Each one of these functions help each other succeed. Then comes design review. Design review is privacy and security should be as early as possible in the design cycle. Means when the developers start thinking about building something, the group of the privacy or security group should be involved from the get-go, should be involved in looking at the design, suggesting how something should be developed, what flags should be turned on, what identifiers should be eliminated or not, what data should be collected or not. Start with the zero data concept. What that means is you start with zero and then you build the data on top. Why? Because then you can decide what data to eliminate and what data to keep. Versus today, unfortunately, companies, what they start with is we have large sum of data. How can we make something out of it? that's actually the wrong approach to it. Vendor due diligence. What I mean by the word vendor due diligence here is not only vendors such as the one you would actually go buy something from, but somebody that you work with, such as downloading an SDK or calling an API, talking to them. Well, you need to know what are their practices, what are their development practices, what are their security practices, what their privacy practices, and put them on a pedestal that you put yourself on, and actually make them monitor what they're doing so they can report that back to you. So it becomes a responsibility, equal responsibility between the two parties. Then security requirements. These are security requirements that driven by default to the development community so they can start baking it from the get-go, from zero. Means if I want to store a password, well, you must hash the password, and here's how hard the password should be hashed. If I want to use an identifier, keep that identifier on the client. Don't move it over to the server. So you put all those requirements in place where then it's no more questionable, no more you're leaving it as an option for the developer to make a decision. That's a hard thing to do because it's almost like you're backseat driving. You have a driver and then you have the backseat driver, and the backseat driver is telling the driver where to go. That leads to a disaster. Threat models. What threat models is really is once you feel you have a tangible a product or an app you're building, you want to sit there and think of how does a malicious actor actually attack that product or that application? What are they going after? Do they go after the identifier? Do they go after the combination of data, such as what Daniel mentioned is, if you combine the identifier with the other data, now I actually can pinpoint who that person is, versus if each one of them kind of separated, then that's difference. And you know, if in another classes we can talk about a concept called differential privacy, which actually allude to the point of making it harder to put that data back together. Then there's also the data inventory, which we talked about, which allows us to actually govern. Then scanning for security issues. There are a lot of tools nowadays that scans for security issues in the code, such as turning on the identifier. Did the developer forget to turn on the identifier or turn off the identifier? Code reviews, obviously, it's the same thing, looking at them, and penetration testing, such as bug bounty programs, such as actual pen testers that they will go and try to break your app or your mobile app and return that value to you, tell you, hey, here are the possible scenarios that someone will break the app. Vulnerability management, obviously, as Daniel also alluded, is things keep on progressing, moving, and getting bigger, faster, and better, I guess. And so with that also comes a responsibility for us to keep things secure and vulnerability free. And the way you do that is by constantly patching, updating the systems, because obviously not every system gets updated to the newest and the latest. Security updates, that's a concept we put in place that exists all over, is over-the-air updates and making it mandatory and making it faster and making it better. Prime example, how Apple treats their update versus how Android treats their update. Apple forces you automatically to get the updates. You just have to say, yes, I want to update, and you get updated. Once you neglect it, your phone starts to kind of getting a little tired, versus on an Android, obviously it's not controlled by Google. It is controlled by someone else, such as the telecommunication providers. Therefore, some Android devices will have a super old Android OS versus a newer Android OS. Same thing even when you're building a mobile app with other products. It doesn't have to be just an OS base. There are changes, such as Bluetooth version changing, getting better, communication within the system getting better. What you want to do is you want to keep on top of it and be able to update it. And with that, I think it concludes my presentation.
Thank you so much, Ferris. This is very interesting. Very, very quickly, if anybody has any questions, or Daniel, if you have any really brief follow-ups, I don't want us to go too far over, but if you have anything else you want to add before we wrap it up?
No, but thank you very much.
Okay. Ferris, can you hand the presentation back over, and I can speak to our next session. I want to thank you both for joining us today. This has been incredibly informative, and I hope everybody else enjoyed hearing from both of you as much as I have. Our next masterclass session will be the 6th session on biometric data. Please check out the website for information on the scheduling of that. It should be sometime this fall. And if you've signed up to receive our emails, you should receive a notification that way as well, fpf.org/classes. And if you have any questions, comments, concerns, feedback, please send them to us at our email address, info@fpf.org. And with that, I thank you all for joining us today.